Hello students, and welcome back to Chemistry A. This is Ms. Sleight, and today we're going to be talking about nuclear radiation, one of my personal favorite topics in chemistry. So first off, what is radiation? Because there's a lot of ideas and thoughts and pictures that come to mind when someone says radiation. Typically it's things like Godzilla, or the Teenage Mutant Ninja Turtles, or Chernobyl. But really, radiation is a very broad and general term. Radiation is simply energy released in the form of particles or electromagnetic waves, which means any form of light is radiation. Radio waves, microwaves, infrared, even visible light, they're all forms of radiation. Now, you might have always thought of radiation as always being harmful. However, hearing that visible light and radio waves are radiation might have you confused. That's because there's really two types of radiation. There's radiation that is harmful, which is called ionizing radiation. Ionizing radiation has enough energy in it to strip the electrons off of atoms and molecules. And this can be very harmful because when you're ripping electrons off of atoms, you're disrupting the atomic structure, and that can be very harmful to cells and the DNA inside your cells. On the other hand, there's the harmless radiation, which is called non-ionizing radiation. And it's just radiation that doesn't have enough energy to remove electrons from atoms or molecules. And it's pretty much harmless. On this chart, we can see that non-ionizing radiation accompanies most of the electromagnetic spectrum. So radio waves, microwaves, infrared, visible light, and a little bit of ultraviolet all counts as non-ionizing. These are all things that are not going to be harmful to you. Some types of ionizing radiation are some ultraviolet rays, X-rays, and gamma rays. Those are all types of radiation that can be harmful to you. The type of radiation that we're going to be looking at specifically here, though, is nuclear radiation. And that's radiation that has been emitted by some kind of nuclear reaction. And pretty much all nuclear radiation is ionizing. So we are going to be talking about some of the harmful forms of radiation. But first, let's talk about sources of radiation. First off, there's radiation all around you all the time. It's called natural background radiation, and we all receive a small amount of it over the course of a year. And there's not really any scientific evidence that shows this small amount of radiation is harmful to us. For the most part, it seems our bodies have adapted to being able to live with it. Now, the radiation that we receive over the year can come from a variety of sources. Some of these sources are natural. One of the biggest sources of radiation, in fact, is natural, and it's radon gas. Radon gas is produced when uranium isotopes decay in soil or rocks or even water sometimes and become radon gas. It makes up probably at least half of the total radiation that anyone receives during a year. Other natural sources of radiation include elements in the Earth's crust, such as thorium and potassium, which means different areas of the Earth will have different amounts of background radiation. We all also receive a very small amount of cosmic radiation in the form of gamma rays and X-rays that come from space, although most of these are absorbed by the Earth's atmosphere. And lastly, we all receive natural radiation from some of the food that we eat, mainly in the form of radioactive carbon. Some sources of radiation are also man-made, though. One of the most common ones is medical procedures. If you've ever received an X-ray or a CT scan or anything like that, you've received a small amount of radiation. Some consumer products release radiation, such as smoke detectors, cigarettes, gas lanterns, and many more items. Most of these are only contributing to a small amount of your overall radiation dose. The amount of radiation you receive is also dependent on your elevation. So the amount of air travel that you do also affects how much radiation you'll receive during the year. Mining and ash burned from coal also produce radiation. And lastly, nuclear reactors and the facilities involved with creating fuel for them also release a small amount of radiation. Now let's get a better picture of what a yearly radiation dose really looks like. So in the United States, the units used for radiation are rems. However, the SI unit for radiation are sieverts. Luckily, it's easy to convert between the two because 1 sievert is equal to 100 rems. The average yearly dose of radiation that people receive in the US is 620 rems. So we're going to go to the EPA radiation calculator, and we're going to go through and see what my yearly radiation dose would be. And I'm going to include this link in the description of the video if you'd like to check it out and see what your yearly radiation dose would be. So this is the EPA's website, and this is their calculator for calculating your yearly radiation dose. All of the radiation is in millirems. And we're just going to go through and look at the questions that they have here. And since it's just the start of 2020, we're going to do this for my 2019 year. So first one is from medical. Have you had an X-ray or nuclear medicine or other diagnostic imaging procedure in the last 12 months? I have not. What region of the US do you live in? We live elsewhere, in Michigan. Cosmic radiation. What is the elevation in feet? A quick Google search will help you find this, and you'll find that Lansing and Grand Ledge are both well under 100 feet above, or under 1,000 feet above sea level. Internal radiation from food and water, they estimate that as 40 millirems for everybody. Do you have porcelain crowns or false teeth? I'm going to put that as a no because I do not. How many miles have you traveled by jet this year? 1 millirem per every 1,000 miles. Well, I made a trip to Boston this last summer, and a round trip to Boston is 1,560 miles, roughly. How many times did you go through a screening machine at the airport over the last year? Well, I did it twice, so put in a 2. Are X-ray luggage inspection machines used at your airport? Yes. 0.002 millirems. Not a lot coming from that. Do you use gas lantern mantles when camping? I do. So another 0.003 millirems. If you are a radiation worker, enter your annual exposure here. All right, well, I can skip that part. How many packs of cigarettes do you smoke per day? 0. I do not smoke. Everybody gets 1 millirem from weapons test fallout. Do you live in a stone, brick, or concrete building? No. Living in stone, brick, or concrete gets you 7 millirems, though. Do you wear a luminous wristwatch? No, I do not. But that would give you 0.06. Do you have a smoke detector in your home? Yes, I do. That's 0.008 millirems. Do you live within 50 miles of a nuclear power plant? No. Do you live within 50 miles of a coal-fired power plant? No. Before I change these, though, I think it's very interesting to note that living close to a coal-fired power plant is going to give you a much higher radiation dose than being next to a nuclear one. That is not what you would expect, would it? All right. Next up is radon. Have you had your home tested for radon? No. If you do not have your radon results with you, or if you have not tested your home yet, you can use the EPA's radon data for the state you live in. So we're going to select Michigan. And living in Michigan on average, we get 303.84 millirems of radiation each year. So that puts my total radiation dosage for the year at 420 millirems, where 72% of that is coming from radon. So my total yearly radiation dose is a lot less than the US average. Now that we've talked about sources of radiation, let's talk about how radiation is actually released? What causes it? And there's two main ways or reasons that atoms emit radiation, and that's radioactive decay and fission. In class, we're going to focus mainly on radioactive decay, but we will also briefly discuss fission in this notes. So, radioactive decay. Some atoms of elements have a ratio of protons to neutrons that simply is not stable. It puts them at an unusually high energy level. Radioactive decay occurs when unstable nuclei lose energy by spontaneously emitting radiation. So spontaneously releasing particles or waves to get to a lower energy state and to become more stable. So radioactive decay is classified typically by the type of radiation that's released in the reaction. And there's three types: alpha, beta, and gamma radiation. We're going to go over the details of each type. First off is alpha radiation. When an atom undergoes alpha decay, it releases slow-moving particles that contain 2 protons and 2 neutrons. Basically, the nucleus of a helium-4 atom. This means that it's going to be positively charged. And because alpha particles are relatively large and slow-moving, they're very easy to block. They can be blocked by something as small as a sheet of paper or the layer of dead skin cells on your body. This means atoms that release alpha radiation aren't typically dangerous outside of the body. However, if you were to ingest them and they release their radiation inside of your body, it could be harmful. The symbol for alpha radiation is either the Greek letter alpha with a mass number of 4 and an atomic number of 2, or the isotope notation for a helium-4 nucleus. Both work perfectly well. One example of alpha radiation is the fact that radium-226 will decay into radon-222 and an alpha particle. So if we write it as an equation, we show radon-226 becoming an alpha particle and radon-222. And we'll be going over more in depth how we write these equations later on in the notes. Next up is beta radiation. When an atom undergoes beta decay, it releases a fast-moving free electron. This means that beta radiation is negatively charged. And while it's more penetrating and more ionizing than alpha radiation, because it's smaller and faster, it can still be blocked by something as simple as clothing or aluminum foil. So again, beta radiation typically isn't dangerous if it's outside of your body. But if you were to accidentally ingest it, it could be harmful. The symbol for beta radiation is the Greek letter beta with a mass number of 0 and an atomic number of -1, or the same mass number and atomic number with an E. The mass number of 0 represents the fact that an electron's mass is so incredibly small when compared to that of a proton that it's essentially 0 mass. And the -1 represents its charge. An example of beta radiation is when carbon-14 decays to form nitrogen-14 and a beta particle, which in equation form, you can see the reaction in isotope notation. Lastly, we have gamma radiation. And gamma radiation is high-energy electromagnetic waves, which means it has no mass and no charge. This is the very dangerous type of nuclear radiation. It usually accompanies an alpha or a beta decay, but because it has such high energy, it easily passes through the human body and therefore can damage cells and DNA when it does so. It's also much more difficult to block. To block gamma radiation, you need at least 3 feet of concrete or 6 inches of lead. The symbol for gamma radiation is a 0 for the mass number, a 0 for the atomic number, and the Greek letter gamma. An example of gamma radiation is uranium-238 will decay into thorium-234 and will release an alpha particle and gamma rays. So this looks like an alpha decay, but they've also added the symbol for gamma radiation at the end as well. Now let's talk briefly about nuclear fission, because this is another way that nuclear radiation is released. Nuclear fission occurs when a neutron is fired at a very large nucleus, causing it to split into two smaller daughter nuclei. This process is used for two main reasons. One, it's used in nuclear weapons, and two, it's used in nuclear reactors. The main difference between fission and radioactive decay is that radioactive decay is a spontaneous process. These isotopes are just naturally unstable and will eventually release their excess energy. Fission is a man-made process that we have to initiate with firing a neutron. Lastly, let's talk about how to write nuclear decay equations. Now, to do this, you're going to want to have your periodic table handy. Alrighty, folks, now let's look at some examples of nuclear decay equations. Our first one is write an alpha decay equation for radon-212. So radon-212 is what we're starting with. So we're going to pull out our periodic table, find radon. It's got the symbol Rn, and it has atomic number 86. So we're going to write the isotope notation, Rn, atomic number 86, and the 212 at the end tells us the mass number of the isotope. So 212. This is undergoing alpha decay, so that means one of our products is going to be an alpha particle. And then it's going to form a new element. Now, the thing to remember with when you're trying to figure out what new element is being formed is that your total mass number and your total atomic number will be conserved in the reaction. So when I'm looking at this, I'm going to ask myself, what plus 2 will give me 86? That's going to be 84. So I know the atomic number is going to be 84. So I'd pull out my periodic table. Element 84 is polonium. So I'd write my symbol, PO. For the mass number, well, what plus 4 will give me 212? 208. And that is the alpha decay equation for radon-212. Our next example is, again, write an alpha decay equation for bismuth-212. Well, we're going to start by writing the isotope notation for bismuth. Find bismuth on your periodic table. It's got the symbol Bi. It's atomic number 83. And they tell us its mass number is 212. Take a moment now to pause the video and see if you can finish the rest of this equation on your own. All right, let's see how you did. It's alpha decay, so one of our products is going to be an alpha particle. Now we have to figure out what the new element formed is going to be. Well, what plus 2 will give me 83? 81. So I'm going to find element 81 on my periodic table. It is thallium. And what plus 4 will give me 212? Well, that's going to be 208 again. And that's the alpha decay equation for bismuth-212. Let's look at some beta decay now. This one is beta decay for iodine-131. Again, we're going to start by writing the isotope notation for iodine-131. So iodine, right here, has the symbol I. Its atomic number 53. So I'd have an I atomic number, and then 131 is the mass number. If it's undergoing beta decay, that means one of our products is going to be a beta particle. Again, our total atomic number and our total mass number should be conserved in the reaction. So when I'm figuring out what element is formed, I'm going to ask myself, what plus negative 1 will give me 53? Well, since it's a negative 1, it's got to be 54. So this is one of the key differences between beta decay and alpha decay. In alpha decay, the new element will have a lower atomic number than the original, but during beta decay, the new element is going to have a higher atomic number than the original. So then I pull out my periodic table. We got to find element 54. It is xenon. And since the mass of a beta particle is essentially 0, our mass number remains unchanged during beta decay. So in this one it says, again, write beta decay equation for bismuth-212. Again, we'll start by writing the isotope notation for bismuth-212. We just looked up that bismuth had an atomic number of 83. Now take a moment to pause the video and see if you can finish the rest of this equation on your own. Alright, let's see how you did. Since it's beta decay, one of our products is going to be a beta particle. To figure out the new element, what plus negative 1 will give me 83? Well, that's got to be 84. If we look on the periodic table, element 84 is polonium. And our mass number will remain unchanged during beta decay. So that's how you write nuclear decay equations. I hope you've enjoyed this note set as much as I have, and I'll see you next time.